Other one is March 17th. All right. It was a very eventful day. Lots of data collection today. I feel sore on my legs. And also did some field work to check out the sensors. And took our cat to the vet. So it's got a lot done today, so I feel good. All right, let's take a look. We have the third day in a row, right? The 3 days in a row we've done something with parentheses. This one was done back in 24. This is about a year ago. All right, let's see. Given a balanced parentheses, S, return the score of the string. The score of a balanced parentheses string is based on the following rules. This has score 1. AB has score A plus B, where A and B are balanced parentheses strings. This has 2 times A. Okay, so basically every time 2 times A, where A is a balanced parentheses. Okay, so this one would be 1, because inside is 1, so this one is 2. And this is a 1 plus 1, that makes sense. All right, so what are we looking at this one? So basically, if we start pushing, right, usually it's on a stack. Think about a stack. Is it guaranteed to be balanced? It's guaranteed to be balanced, okay? So what? So we push in the left parentheses, we push in the second left parentheses, we push in the third parentheses, and then we have whatever string is in the middle. And then whenever we have a right parentheses, it only consists of the left and right. So the first time a right parentheses comes in, that will be 1. We push the 1 into the stack, right? And then we come again, if there's a value in, then we just double times 2. That'd be 1. Yeah, we push it in. 1 push it in, and then eventually we add up everything. Okay, let's try this method. All right, so what we're looking for here is, of course, we start with this, and then we say stack. It's going to be this, right? And then we say for C in S, right? If C is equal to a left parentheses, then stack.push, append C. Else, so it's a right parentheses, and then what we're gonna do is if stack, the top of stack is equal to a left parentheses, right? Then we're gonna say stack.pop, right? And then stack.push. Do they have like push pop? I don't know. Oh, no, they don't have. It's not a stack. Come on. It has append. Append 1, right? That's the score. Else, if it's not a left parentheses, then it must be a score. And then we simply say stack dot pop twice. So score equals stack.pop, and then stack.pop, that's pop the left parentheses, and stack.append 2 times score, right? So we'll do this, blah, 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 and it's perfectly fine if we do this. Elif. Right, elif, we do this, and then finally, else, we do this. Once we're done, we're going to return sum stack. All right, let's check the results. So we have this is 1. Yeah, remember this is 2, and this is 2 as well. This is S score of S. All right, they do pass, but let's throw in something more complicated. As the length is only 50, that is a little bit troublesome. So I don't know what that means. So we can do a lot of this, right? And then within, let's do a lot of this. Within, a lot of this, a lot of this, right? And then within this, we do a lot of this. Just try it out. S is not balanced. What? Oh yeah, it's not balanced. Did you see balanced here? Now I think like I have to do this to balance it. Try it again. Ooh, we have issues in this. That is interesting. How? I mean, something's in the stack. How is that possible? It's a good test case that we created. I don't know what this is. So let's just run it. Okay, that's fine. Let's just, I don't know, print stack at each step. Left, right. Left, left. Oh, we have this situation. You see that as a 1, and then I've got to have parentheses, and it becomes 1. Now I have to merge. I see. So this is fine. Else, change this while stack and stack. Well, it's actually, it will always have stuff. While stack minus 1 not equal to a left parentheses, right? Then when I pop it, attitude would be stack. We can just say if this, else, right? And then we say score is equal to 0. Now while this is not, score plus equal to stack.pop, right? And it's not it, pop, 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 pop. Once we're done, then we're gonna do stack.pop and then stack.append score times 2 specifically, right? Oh, hold on. What about this situation? Score will be 0. So what we can do is a maximum of score times 2 and 1, like that. So all of this is not necessary. Then we run it. Then we get this. All right. Well, it's much cleaner. All right, I'm gonna go with this. Yeah, confidence. Let's go. Yep, that is correct. It must be a better solution. Maybe like without using a stack. I don't know. You can do this without using a stack? Doesn't feel like that way, right? Alright, so we say I use a stack to keep track of left paren and the most recent score, right? And each time a left paren is encountered, push it into the stack. Otherwise, we keep popping the stack until reaching a left paren, and all the popped elements are scores, right? Are scores of the parens contained within. Thus, sum them up, and then then multiply it by 2 before pushing it back to the stack. And the result when 32. I just realized we can save an operation of pop. Right? I don't have the pop. We just need to be this minus 1 equal to. Alright, we don't have to. We're going to save a pop. If you think about it, else, right? If it's not, it's a value. And now I'm on the right. Then what I do is I will pop this, become 1, and then I will add it to that. Hold on, we might be able to do it even better. Yeah, we append, and then else, right? What we say is if it's a right parentheses, there are only one situation is, no, two situations. Is either it's a left paren or it's a number, right? If it's a number, we do so. You know what? Hold on, this is a 1, right? I feel like I have another idea. Further reducing the number of, pops we need to do. So yeah, this is all fine. So we just say aleph, right? C is equal to, no, not C is equal to stack minus 1 is equal to a left paren. Then we pop the left paren and check what it is, right? We say stack dot pop this left paren, and then we say if stack minus 1 is equal to a left paren, then we're gonna append. Oh, this feels convoluted. Nah, this feels convoluted to me. I don't like it. Let's see what I got last time. Oh, 3 solutions last time. Curious. Count cores. The onion solution. Yes. That's true. Counting onions. Layers. Else layers minus equal 1. If S so layers plus 1, and then layers minus 1 if to the left we have found the core, then rest plus equal to 1 to all the layers. And then we'll keep going, it's going to be right. Oh, then with layers minus 1. Oh, Ooh. How smart. So smart. Oh, layers, yes. Because the center, that's 1. And the layers we can increment and decrement. I remember this one. Okay, layers is a good solution, huh? What is this one? We don't sum. If it's a left parentheses, we append a 0. Look at this. We append a 0. Otherwise, it's a right parentheses. So we'll pop. That will be the score. And so we pop it. We're going to say this. If score is 0, we plus 1. Otherwise, 2 times. Oh. So we don't have to push. We don't have to push this the left parenthesis. That makes sense, right? Like here, I have a mixture of string and integer, but in fact, the string is not necessary. Left parenthesis just means a 0 score, and then once we found the right parenthesis, that will be the score. That's like the score contained inside. And if it's 0, it means we don't have score. Then we just plus 1. We just use 1. Otherwise, that is the previous one, right? And then we add to the previous one. Nice. Ooh, so good. So good. All right, this is my original solution. Ha. I did not improve at all. That's exactly the same, exactly the same solution I had back then. Well, I avoid another pop. That's exactly the same. So nothing has changed in me. Nothing has changed in me. That's exactly the same solution. So I think this just means those two solutions are way out of my league. Right? That's out of my league. But how do we even figure that out? Yeah, stack is the easy one. Counting cores. I like counting cores, but I'm pretty sure this is a bit hard to do, but I did hope that I can actually get the stack correct. And if you think about it, it is like, you see, I append the left parentheses, and then I set the score to 0. It didn't occur to me, I can just append 0, right? And just keep adding to the last of the stack. I don't have to do any of these while loop. Basically, I just pop it, and then do, damn. Let me write another one. I'm not sure. I'm not gonna write accounting. Maybe we should write that too, just for the sake of it. So this will be a better stack solution. I have demoed this a year ago. So stack this if this when append 0, right? Else when I say score equals stock.pop, right? And then stack -1 plus equal to 2 times score, all right? If score else 1. Yeah, just make this more explicit. And we have to go initial is 0. Then we just need to return stack 0. Nice. All right, and then the last one. 61. Doesn't matter. Onion. All right, onion will have rest is 0, right? And layer. Yeah, we'll have a less than layer. Both are 0. And if this layer plus equal 1, else, all right, then layer minus equal 1, right? And the fs I minus 1. Yeah, we have to do I. Say enumerate. If that is equal to a left parentheses, that means we have hit the core, right? Hit the core. So rest plus equal to 1 left shift layer. And then we return rest. Very good. All right. Switch gear. Design circular deck. Oh, nice. Good question. I immediately like it. Design a circular double-ended queue. A circular double-ended queue. Okay, maximum size k. Insert front, add an item at the front. Insert last. Rid of the deck. It is true, false. Delete front, delete last. Get front, get rear is empty, is full. What do you mean by circular deck? What does that even mean? Circular deck. Wait, what's the capacity is 3, right? Okay. Insert front. So insert. So we have 1, 2, 3. So it's 3, 2, 1, right? It's 3, 2, 1, the whole thing. Insert again, well, we have 4, so that's bad. Now we shall get 1. Wait, get 2. Wait, hold on. Oh, insert last. Hold on. Insert last was 1, 2, 3, 3, 1, 2. It's 3, 1, 2. Okay, rare is full is true. 3, 1, 2. 2 got deleted. Insert front, so that's 4. Oh, that's what circular means. That becomes 4. Front is 4. 4, 3, 1 becomes. I see. Okay. Well, linked list. Right? Just linked list. We can do linked list with guarding a dummy nodes at the front and back. So we have 2, right? So we'll always, it's actually a doubly. Now we can do a doubly linked list. A doubly linked list with a front dummy and a tail dummy, right? So the front and back will stay the same. They don't have to move. And then when I insert to the back, we just push into the back. Instead of front, push into the front. And delete back, delete front can all be done in O1. Get rare, get front is all do O1. Is empty, we'll keep an internal count of the size. Is full. Yep, got it. Yeah, I was a little bit afraid of this term circular. Like, what the hell is circular? Well, it turns out circular, I think, just means if you don't do it, right? If you don't do it in a doubly linked list, I do think you have to think about it's going to be a circle, right? It's going to be a you can actually try that. You can actually try that to do it on an array, right? So we can push it to the back. So we start from the front. We start up front. What if we push it front? We need a calculation on the indices, right? So push it back, it just the index moving back. Push it front, we go to -1, but we don't do -1. What we do is the current thing. Well, -1. This thing, the current index, -1 plus the length, right? -1 plus the length. So if a -1, if the length is 3, and -1 plus 3 is 2, so we go to the end, right? And we're pointing here. And then we go -1, so that's 2. 2 minus 1 is 1. 1 plus 3 is 4. So it's actually this -1 and a mod, right? I'm going to be +1 mod and then -1. -1 plus length mod. Or +1 and then mod. Yeah, maybe we can do that as well. And we also keep track of the size. Well, technically we don't have to keep track of the size. But just see if the 2 pointers are if I want to insert, then when you compute the next index, if it overlaps, then that means it's bad. You know what? This might be a better idea than, doubly linked list definitely is the easiest idea, right? Easiest idea. We can actually try both. Which one I want to try first? I want to try the doubly linked list first. It's more fun, right? I feel more fun. So say dlist, doubly linked list. I'll just call it node. Too lazy. Node, what do we need? We need a value, right? I should just do this. Def initiate val, right? That's the only thing I need. And then self.val equals val. Self.next equals none. Self.prev equals none. Okay, that's the node. So I initialize with self.cap equals k. All right? Yeah, with decrement the cap. Oh, and self.head equals a node okay, so val equals a value is not going to be taken. Value 0 is -1. All right, equals -1. So we can node and self.tail equals node, right? And then we need to do self.head.next equals self.tail, and self.tail.prev equals self.head, right? We'll connect them. Now in insert front, so every time you insert front, we're going to say if not self.cap, then we return false, right? Otherwise, self.cap -1, and then we insert, right? How do we insert? We say, we get a new node equals node, val equals value, right? And then we say self.head, actually we say node.next equals self.head.next, right? And node.prev equals self.head. So we handle this. Node.next pointing, node.pre pointing, and then self.head.next equals node, right? And then node.next.prev equals node. That's it. That's insert. Now insert last, very similar. So we'll write the similar code. Self-cap node equals this. Now we're gonna say node.next equals self.tail, right? And node.pre equals self.tail.pre, right? And then self.tail.prev equals node, and node.prev.next equals node, right? So we handle this. Delete front. If oh shoot capacity if node capacity, if no capacity we cannot add. So if how do I know? Oh, if it's 0. If capacity is a current capacity, right? Current capacity is K. I think I'm wrong. This is have to if self.cap. No, wait. Capacity is how much left, right? How much left? Yeah, it's not. It's mean nothing, no capacity left. And this is if the capacity is empty, so we have full capacity, right? If we have full capacity, which just means, if you think about it, it just means if self.head.next is equal to self.tail, right? Then we return false. That means there's nothing in there, right? Otherwise, we're gonna do self.cap plus equal 1. And once we do that, and then we're gonna delete front. So we just say self.head.next a node. This is the node, right? Node is this. So we want to delete this node. So we say self.head.next equals node.next, and node.next.prev equals self.head, and we can say node.next equals node.prev equals none. Kind of delete it. Okay, so that's delete front, and when delete last, similar thing, capacity plus equal 1, node is going to be tail.prev, and then we just say tail.prev equals node.prev, and node.prev.next equals self.tail and node, right? So that's that. get front, if nothing, capacity, right? If there's no capacity, then return -1. No capacity. Not no capacity, we'll have nothing. Nothing to give. Right? Nothing to give. Otherwise, we can give the front, so just return self.head dot next dot value. Right? Rare is the same thing. If this, nothing, otherwise self.tail dot prev dot val is empty. Well, is empty is return this, right? Return this is full, return self.cap equal to 0. And I just realized I can actually say if is full, right? Right, not this. If self.is is full. If self.is is full. And here just if self.is is empty. Yeah, that's how we're supposed to use it. No repeating. All right, so that was my first solution using doubly-linked list. Let's run it. None type has no prev. Where? Huh. That is funny. Note.next equals self.head.next. Note.prev equals self.head. This is all correct. And then self.head.next was node. And node.next should be self.head.next. .prev, it says, has no prev. Huh. Someone is not correct. I feel this one's right? Self.head.next equals to new node. That's a new node. And node.next is self.head.next. So node.next is this one. And then this one, the pre, that's correct. All right, let's see this one. When insert last, so node.next equals self.tail. Okay. And node.prev equals self.tail.prev. Makes sense. Oh, head. My bad, tail. Self.tail.prev equal node. And node.prev.next with node. Okay, let's see if I make the mistake in other things. Delete tail. All right, this one shall be right. Oh my god. Did I get this one wrong? It's empty. If this is equal to this, then we say it's empty. That is not right. Because initially it is empty. But Wait, hold on. I return false. I can't even insert one of them. If is full. Yeah. Insert last. Insert last. We first check if it's full. And when call is full, it's self.cap equals to 0. And self.cap is k. K is 3. So should be false. Is full is false. So this is false. Huh? What? Oh, I think I know what happens here. I have to return true, otherwise it will return a null value, which is considered false. Got it. Int, boolean, okay. All right, that's my, yeah, this one should be right. Come on. There we go. So, well, is this the fastest? Probably no, but that's an interesting implementation, right? So use a doubly linked list. This problem is not very hard. All right, so all operations is in O1. This one is 108, 43. All right, now is the real challenge. How do I reset? All right, now is the real challenge. I want to use a list for this. Okay, so we just simply say self dot deck equals 0 times k, and self dot head equals self dot tail equals 0. Wait, hold on. Do they all point into? Let me think. What does this mean? Front and back. This actually is front and back, right? So the back, append, we keep going. The front, we keep going, and the front always go left, back always go to right. So initially, if I add one to the front, so the front will always add it and then go to the front. That's an interesting case. Do we add first? If we're in a position where we're preparing to add stuff, so that position is open, and I will add to it, and after that I'll move to the next position that's waiting, right? So if I add this one will go front. What if I push to the back? So in my mind, the front and back should be like this, right? We add one, we go forward. So the capacity is interesting in this case. me draw it out. Capacity is 3, right? If we do just 3, and then we set front and back and point in the same thing, that's not going to work. So pushing it in, then what? Front goes here. Where does the back go? Back goes here. Doesn't make any sense. Alright? But it has to be front and back are occupying separate cells. So now, we say we're gonna insert last, so we insert 1 here, and the back goes here. Insert last 2 here, and the back goes here. And then insert front, so we insert front. Now I kind of remember I had this in my algorithm class, and now F and B, they meet each other. So whenever they meet each other, that's bad, right? And then we want to get rear. Get rear is just, okay, front and rear. Now front and back. Get rear is back. Back plus 1, that's the rear. And then is full is if they meet each other, that's full. And then they will delete. How do we delete? Oh, delete is just gonna be this one move back to here. That's delete. And if we delete again, delete again. So it's empty if the back is front plus 1. So that means this has to be k plus 1. Right? And then let's just say self.front equals 0. Self.back equals 1. Right? That's our starting position. And self dot cap equals k. Because we have to do the mod, unfortunately. So insert front. We say if let's do is empty. Return self.f plus 1 equal to self.b. Of course, this one we have to mod self.cap. If it's equal, front plus 1, that's this. Return self.f is equal to self.b. Alright, so we need to say if self.is is full, return false. Otherwise, it's not full, so we insert in the front. So it's self.f equals value, and self.f equals self.f minus 1 plus self.cap mod self.cap. Insert last. Again, if self is full, then what do we do? Otherwise, we say self.back equals value, and then self.back equals self.back plus 1 mod self.cap. Delete front if, wow, look great. Self.is empty. Return false. Oh shoot, I have to return true, man. Return true. Okay, if empty, return false. Otherwise, when delete front, we basically just say self.f plus equal 1 equals self.f plus 1 mod self.cap and return true. If self.is empty, return false, and then self.back equals to self.back -1 plus self.cap mod self.cap, return true. Get front, return self.f. Or if self.is is empty, return -1. Else return self.. I just realized something's wrong. Hold on. Self.deck. Jesus, man. Self.deck. This is fine. Yeah. Get rare. Again. This is gonna be .b. All right, let's try this one. Yeah, just for fun, I use 2 different methods. Let's see. Ooh, that's pretty bad. Okay. All right. What happened? Is empty. I feel instead of introduce another one, I like to change it. Every time I say self.cap. All right. Changing to len self.deck. Try again. Almost. So I was able to push 3, but when I pop up 0. Oh, shoot. My bad. It is wrong because when I get front, F is pointing to the place that I can push things in, right? So it has to be, oh, dear God, +1. It's this. Thanks. I'm not pointing the right position. Yep. Try this. Oh, look at this one. Much faster. Much faster than the doubly linked list implementation. This one uses a single list by performing index wrapping around. We are able to keep 2 pointers, right? Always pointing to the next position for adding values. In this setup, we can tell emptiness by checking f plus 1 equal to b, and fullness by checking f equals to b. Of course, all the plus or minus index arithmetic, I think this, must go through modulo. Right. There's also O1 for each operation. But this one's fast. 68. 96. Pretty sure this is what the standard solution. Rain buffer. Facebook interviewers really loves it. Yeah, it is a rain buffer. Yeah, it's the same thing. It's a very classic thing. I have definitely learned this, right? Definitely learned this in my earlier algorithm class. I remember this. All right, that'll be it. I will do another one very soon. Adios.